Ja, ich glaube, es kommt jetzt mehr der schwierigere Teil. Ja, also wir hatten ja hier die Formel, das war in der komplexen Konjugation, die Eulerzahl von xc gleich durch die Spuren auf H2K plus. Oh, sorry. Yeah, we had already the formula that for complex conjugation, the Euler number of the fixed point set is given by the traces when the complex conjugation operates on H2K plus and H2K minus. Now we assume that we have a complex conjugation, let's say, on with a Kähler metric, which is even invariant under the complex conjugation, and then the main thing is first step that we use the splitting of H2K in the direct sum of HPQ. P plus Q is 2K. Yeah, we have complex manifold of dimension 4K, so that the middle dimension is even, and this is the homology group. And then this can be split off in terms of the HPQ. And the complex conjugation maps, or it must be very rough, maps HPQ in HQP, and HQP again in HPQ backwards. So, if P and Q are different, the trace, so to speak, restricted to this case must be 0. Therefore, it is already clear that the contribution to the trace only comes from HKK. And HKK we can again split into the positive part, cohomology classes in HKK, where the square, the cup product square, is positive and integrated over the fundamental cycle. So we now can improve our fixed point theorem in the sense that the Euler number of xc is equal, the Euler number of the fixed point set is equal to minus 1 to the k, and then we can write here the trace of HKK plus minus the trace on HKK minus that is, we throw out all HPQs here, but then we have this result. Yeah, but anyhow, the complex conjugation when operating on these cohomology classes, the eigenvalues are only plus or minus 1. So you see, you can, so to speak, think of this as a contribution of plus 1s and minus 1s, plus 1s and minus 1s. So you have to sum here over plus 1s and minus 1s. But the maximum number you can reach is when everything is favorite, in the sense that you cover up with all HKK. Therefore, it is clear that the Euler number of xc is less or equal to HKK of the manifold under consideration. So we are studying a manifold X with a complex conjugation. So you see, this is very concrete result. Now this appears in various places in the literature, very old literature and especially Russian literature. I should mention so many names, but actually that it is generalized to this form, HKK, also appears in the Diplomarbeit with me by Friedrich Goetze, submitted in 1975. And because I spoke on the occasion of his 60th birthday and tried to explain what he did in his Diplomarbeit. I'm not sure whether he still knew it, because he had become a professor of stochastics. Yeah, so in any case, this formula appears also in his Diplomarbeit and appears simultaneously, for example, in a paper by Kalamov, but which was not available to him at the time, because it just appeared and maybe had not been translated and so on. So, yeah, but this formula can be proved interesting enough for the negative Euler number. Because after all, xc, the fixed point sets, can also be surfaces of higher or manifolds of higher genus. Therefore k equal 1, this would be surface. A surface, topological surface, can have negative Euler number, so it's interesting to have an estimate for this negative Euler number. And now I assume that I have a Kähler metric, so we have a fundamental form for the metric, maybe I'll write this here, fundamental form for the metric omega. D omega is 0, so it represents a cohomology class. Omega to the 4k, to the top dimension of the manifold, cohomology class of dimension 2. This is represented by the fundamental form of the metric. So then omega to the top dimension 2k, that would be positive, or we can normalize to 1. So omega k times omega k would be positive. But we also assume that this Kähler metric is invariant under complex conjugation. Then the fundamental differential form of the Kähler metric under complex conjugation will go to its negative. So we also in particular know that C applied to omega to the k, very bad here, you cannot read it. So C applied to omega to the k is minus 1 to the k, omega to the k. Yeah. And therefore, I mean, should not carry this out. There is an element in the middle dimensional cohomology who makes it impossible that for the negative Euler number, HKK is achieved. Follows from these facts for omega. And therefore this, we have here an improvement of this estimate. This of course is true also for negative Euler number, but rather trivial. So this is less or equal to HKK of x minus 2. Yeah, because at one place in the whole split up of HKK, 1 is replaced by -1. And then HKK cannot be reached anymore. And this fact that 1 at one place has to be replaced by -1, this is done by the Kähler form. Yeah. Okay, so let's leave it like this. And so many applications of this can be made. For example, the HKK can be calculated for complete intersections of hypersurfaces in a complex projective space. This you can find in a paper of mine in 1954. Yeah, at the Congress in Amsterdam. So for the complete intersection, in particular for hypersurfaces themselves, the HKK is known. And so then you know that for the real models, we have an estimate for the Euler number, namely in terms of this HKK. And now then you can try to look at applications. Yeah, maybe I first jump ahead and tell you the H11 for a hypersurface of degree m in a projective space. It's an easy formula, but I don't want to calculate it here. But I don't find it. But H11, yes, it's H11 for a hypersurface of degree m in projective space. It's very well known. It is equal to 2/3 m to the 3 minus 2m squared plus 7/3 m. You can again make natural checkups by looking at this. For m equal 1, you must get 1 and it checks. But for m equal 4, yeah, I mean, you can also take m equal 2 and so on and make checks, but for m equal 4, the H11 for a hypersurface of degree 4, the H11 is, yeah, that's the calculation, and the H11 is 20. So, wonderful. So you know that for a real surface of degree m in a real projective 3 space, x degree m, odd or even, doesn't matter in this case, m degree m, in P3A now, a real projective surface, but then the Euler number, yeah, I only take the as estimate for the Euler number itself, maybe is less or equal 20. So you see the real part of this surface could just be 10 balls. Look like 10 boundary supports, like 10 two-spheres, perhaps. Then the Euler number of XC is 20, if you have 10 separate two-spheres. But to have 11 separate two spheres is impossible, because then the Euler number would be 24. Yeah, so you look up a paper by K. Rohn, I think 1911 or so, in some publication of the Saxonian Academy or something like this. There he constructs a surface defined over the real, which consists of 10 balls. So the surface is only the boundary of these balls, of 10 balls. And I think he also claims to prove that 11 separate balls are not possible. Yeah, but this was also, we also proved it now. But I mean, this is the proof is some by other people. In particular, perhaps I should mention the Russian mathematicians. Petrovsky, already in the 30s, have proved such things. Yeah, now I actually wanted to apply it to the case of loops. And if you have such loops, I mean ovals in the plane, a real plane. And for this I wanted to use the curve started from a curve of degree m even in the P to C, and takes the double cover of P to C along this curve of degree m even. Then I had the formulas for the Euler number and for the signature of the surface. Yeah, Euler number and signature. And without telling to you how to do it in the details, these invariants, Euler and signature of a surface, give you also nice formulas in certain cases for the H11. So the time does not permit that I give you these formulas, so I just give you the formula for H11 of X, of this X, for technical reasons I need, I can also give you H1, I need H11 over 2, and no, H11. And then I have that the Euler number of XC is less or equal to this H11. And so I will do this now. Maybe there's still the blackboard. Also, using this method, I get a formula which actually is in the paper of Petrovsky at the end of the 30s, I think. That the Euler number of XC is less or equal to, and then comes the H11, is less or equal to 3m squared minus 6m plus 8 over 4.
So this is now where x is covering over.
Pardon me?
So x is in this situation the covering over P2.
C, yes, we have the curve C, and we take we take the double cover of the projective plane along this curve C.
And C has degree n, so that's
What?
setting. And and C had the degree M. That's the setting.
I don't.
Because C was of degree M.
C was of even degree, M, in order to take then this double cover. So, therefore, this is information, if you like, on a curve of degree M. If we have a curve of degree M, everything defined over the reals and it's smooth, with complex domain, and then we take the complex surface, which is a double cover. Complex conjugation, we have on everything happening there. And now, you see, I said before that the curve C is given by, let's say, by f equals 0. And then we take square root of f. And this function defines to you the double cover. But how does it look like? Assume that we have a certain number of loops, or certain ovals, separate. If we have such an oval, maybe some ovals separate to each other. So then we can take the case that the f is negative outside all this. Then it will be positive here. And then when we take square root of f, but now everything over the reals, there will be no point over here because there is negative here, the f. But it will be positive here, so we take square root here. Yeah, but the square root is some sign, positive and negative. So there is somehow something over here, over every point here, there is a point up here and a point below there. So back the blackboard. There. So therefore this gives a two-sphere. Such an oval gives a two-sphere. So if we have separate ovals, separate to each other, then the number of such separate ovals times 2 is the Euler number of xc. So let us calculate this for m equal 6. Because this is the interesting case. M equals 6, we have Euler number of xc. Can somebody calculate this for m equals 6?
20. 20.
Pardon me?
20.
What?
20. 20.
20. Good. Euler number of xc is less or equal 20. So, if we have a curve of degree 6 with 10 separate ovals, nothing else, then the Euler number is less or equal 20, the Euler number. The Euler number, each oval gives such a two-sphere. So we can have only 10 ovals separate to each other. But a curve of degree 6 has a maximum of 11 components. So the people always looked at such M curves. And therefore this result shows that an M curve with 11 separate ovals is impossible. But the M curve which Hilbert showed had 9 ovals, like this, and then had 1 oval and 1 oval inside. Yeah, but if I now look at the situation, everything is minus here for f, is plus in here. everything is minus in the outside world, so it's plus there and minus there. So therefore, if we take square root of f over the reals, everywhere above here is a point, and also below there's a point. So you get a torus. Its Euler number is 0. Therefore, the Euler number of the whole business is 18. And 18 is less or equal 20, so no contradiction. But we don't have an M curve for which the bound is achieved. Yeah, in fact, usually, I think, at least I have not followed the literature, that is in general perhaps impossible to have an M curve, but the people never looked at curves which are not M curves, so maybe a curve which has just 10 ovals or something like this. Yeah. So, by the way, about M curves, Hilbert gave some other example of such an M curve, and Gutkov later gave a third example and proves that these are all those which are known. And Hilbert also gave some example of a curve of real curve of degree 8, yeah, I hope I interpret his example of degree 8 correctly. And then, yeah, maybe I can indicate it, but there's still a blackboard, yes. If I interpret him correctly, I think Hilbert wrote for n equal 8, there's the following. M equal 8. 17 separate ovals. 17 separate ovals. One oval with 3 ovals inside, and one oval inside one of those. These, how many do we have? 17, 18, 20, 21, I hope. No, 22. What is the M equal 8? We showed by Hannah, 7 times 6 over 2 plus 1. This is 22. 22 components. So this is an M curve, which Hilbert writes down. So these are 6 ovals. Or not? 2. One is missing. These are 6. Yeah, and then if we look at our invariant, of course the function f would be negative outside here everywhere. Negative would be positive here, negative here, positive there. Yeah. And if you calculate the Euler number, which comes out like this, it will be 32. And the H11 limit is 38. So it's still not the best. Yeah. So there is so much classical literature about these things, so many names are involved, in particular from the Russian side, also up to 1975, like Kharlamov. And I have some of the papers here. There's this paper by the American mathematician Mrs. Rugdale, of 1906, American Journal of Mathematics. And then she studies, she has wonderful pictures up to degree 12 for all kinds of combinations of ovals which are possible. Yeah, and so this one can study. And then there is the old paper of Petrovsky of 1938, which I brought with me here as an example. Then there is a survey article in a book published by Peters Publications in 2002 by Benjamin Jandel, about graphs that curve, and he gives a survey about what I talked about. Yeah. Then, das Paper bei Harnack hier über die Vielseitigkeit der ebenen algebraischen Kurven. And then this paper of 1911 by Rohn about die Maximalzahl von Ovalen bei einer Fläche vierter Ordnung. And this number is 10, as was explained by our calculations. So maybe I stop here.
Okay, thank you very much.
Yeah.
If I understand correctly, the distribution of ovals is in general open. So that's
You see?
the distribution of how the ovals can, which configurations are possible, that's in general open. Up to which number of components does one know it now? So what's So you mentioned, I think, what was it? In 1911, he did it up to how many components?
I don't know her first name. Maybe Victoria, let's say, Rackdale. V. Rackdale. She has partial results up to curves of degree 12.
But is nowadays up to degree 12 everything more?
No, I mean what people know is that these estimates are sharp if I don't look only at M curves. I mean, M curves were, so to speak, always the favorite things. Therefore, Hilbert looked at 11 ovals for degree 6. Yeah, so maybe there are many more interesting applications in higher dimensions because the HKK is known, and I only gave you 2 applications, namely for this double cover of a projective plane along a curve of degree M even. This gave an algebraic surface to which one could apply the resultant complex conjugation. And the other example was, in a sense, simpler. One simply took the hypersurface of degree M in projective 3 space and therefore looked at real surfaces of degree so-and-so in projective 3 space. And there already the degree 4 is interesting, to construct one's surface with 10 such components. Yeah, you have to maybe do some work. Yeah, but the literature is available. There are many things in the literature which I do not know at all. Only some of it I explained here. So it's open to further studies.
If that's not the case, thank you very much again.